similar approach to get a better understanding of scene components and how they can be used. We'll be creating a custom scene component that will implement physics to create a hovering mechanic. So to get started, from the components folder, create a new scene component and name it hover component. When that's loaded, navigate to the header file, head to the bottom of the class and create a new private section. Again, we can leave the default functions as we'll be utilizing these in the code file just a little bit later. This time around, we'll be making use of the parent root component rather than the actor class. So remember previously we stored the actor class. This time we'll be using the root component, which is something we accessed through the parent actor class previously. This is just going to give us a kind of idea of how we can work with both. So to get this started, we'll begin by defining a new uPrimitive component pointer, and we'll name this one parent root. Then we'll need a couple of variables to control the hovering mechanics. We'll create one named max hover force, which I'll default to 100 units, and a second float named hover force distance, which I'll also set to a default of 100. These will simply control the maximum force to be applied to move the object away from a surface, and of course the maximum distance in which to apply that force. Then both of these would benefit from a U property to allow us to easily test different setups. I'll set these to be edit anywhere and provide a category named hover variables. We likely won't need any blueprint access for these, so just these two specifiers should be fine. Of course, if you did want these to be accessed in blueprints because it's in the private section, you'll also need to add the meta specifier to allow private access. So now let's move over to the code file, and inside of the begin play function, we can store the parent root variable that we've just created. To do this, we just simply need to get the parent root to be the result of a call to the get owner, and from there we can use the find components by class. So specifying the class type of uPrimitive component should return the result that we're looking for. Then with our parent root set, we can now run our check to confirm that we have something valid to reference. And if we do, we can set the default properties that we want this component to possess. So like in the actor topic where we had some properties that we knew any object would need to have enabled to allow our logic to work, such as being set to be movable, we have some similar properties that we can set from this component that we know that we'll need in any class utilizing this component. So to begin, the most important is to set the set simulate physics on the parent root to be true. As we're going to be using the forces on the parent actor, we won't be able to do that without the physics enabled. So again, anything that uses this hovering component is going to need the physics to be enabled regardless. So rather than having the designers or other people working with this component potentially needing to do this on a per object basis, we'll just do that now. I'll then set the linear and the angular damping to 2 for the parent root. This is completely optional and has default values that would work without being changed. However, changing it here again is just going to ensure that anything utilizing this component will have similar properties that we then know won't be changing drastically between classes, so again we can kind of tailor the functionality within this component. And then finally we can set the max hover force to be the max hover force multiplied by the parent root mass using the get mass function call. Again, this step is completely optional, but this will take whatever the maximum hover force is set to be in the editor and multiply that by the component mass, which is usually around about 100 units or higher. And without this, we'd need to enter a force unit, which would be in the hundreds of thousands, and it just seems a little bit more understandable working with units in the tens of thousands when applying forces. This is especially so when you're working with others who perhaps won't be seeing the code and getting a complete understanding of what's being applied in the background. So for now, we will be coming back to this function a little bit later, and you'll see why. There's a few things that I've left out just to demonstrate a couple of kind of nuances and things to consider going forward. But the updating of our parent actor and whether it should be hovering and by how much will be done in the tick component function. So if we roll down there, the first thing that we're going to need is an f hit result to test against, which I'll just name hit. To fill hit, we'll make a call to the get world, and the line trace single by channel function. And for this, we'll first pass in, of course, our hit, as that's the result that we're hoping to validate. Then next, we can see our first type-specific use of the scene component. So for the trace dimensions, we can actually provide the value returned from the getComponentLocation function call, which, as you might expect from the name, is going to return the location of the component. In a similar way, the endpoint of the line trace that we'll be using is going to be the result of our getComponentLocation. So the same function call again, but this time minus a new vector, which we can set to 0, 0, and then the hover force distance on the z. So this will simply take the location of the component and trace down x units on the z-axis. And to finalize the line trace function, we'll pass in an e-collision channel of ECC_visibility. And with all of that done, we should now be updating our hit variable so that we can check against this and see if it's being blocked by checking the B blocking hit. So at this stage, if this is returning true, we know that we're within the hover force distance, which means we can start to apply that force to our object. So for this calculation, we'll need a few different variables. The first we'll be creating is the location to start from. This is going to be an f vector named start location. This will be equal to the return value, once again, of the get component location. So we can see already by using the scene component in a scenario which is going to be doing a lot of movement or locational based logic, it's going to make things a lot easier rather than constantly passing a call up to the parent object, finding out its location in the world. We can just use everything from our scene component. So for that first variable, we need to then check the ratio between our location and the hover goal. So we're going to create a constant float named distance. This will be equal to the start location minus the hit.location and the size of this encapsulated equation. And then for that ratio I just mentioned, we'll create another const float named ratio equal to fmathClamp. And we're going to want to clamp the distance divided by the hover force distance, and of course clamp it between 0 and 1. And then the final thing to finish our calculation, let's create an f vector named force, which will be 1 minus the ratio multiplied by the maximum hover force, then multiplied again by the hit.impactNormal. So with all of these calculations made, we can call the add force function. Now this was the main goal that we've been working up to, and this is going to be called on the parent root object. So of course, although we can do all of the calculations based purely off of the scene components transform or location, of course this still doesn't have very much relevance in terms of like how things can move around in the world. So we're still going to need that parent root object to be the thing which is having all of the updates for the force to be applied to. So for the force to be applied, we can pass in force, set the socket name to name_none, and then set the B acceleration change or accel change to false. And that's pretty much it. So that would now be a working hover component. Now, of course, the idea here wasn't really to break down how hovering functionality works, but to see some of the scene component specific values that we can retrieve, such as the location, compared to needing to reference the parent actor's location in the previous topic. However, to make this a little bit easier to understand, it won't take long. We can add a couple of debug visuals to our code. So first we can draw the distance that this component is trying to hover using the draw debug line. For this we can pass in again the getWorld as the world context reference. We can use our start location that we've created and stored above, and the line end can be the hit.location, again, which is something we have stored and available from above. And then I've chosen to set the color to white, the persistent lines to false, and the lifetime to 0, as we're running this in the tick function, so we'll be constantly drawing new lines anyway. And then to really drive home what's happening, we can also represent the point of impact using the draw debug point, again passing in getWorld, then the hit.location. I'll make the size of the point 10 units, set the color to black so it stands out just a little bit, and again the persistent lines will be false and lifetime set to 0. And to get familiar with adding some extra flexibility to components, rather than just having this run constantly, we'll nest this inside of an if check, which will be checking a Boolean that we'll go and create in a moment, and we'll call this one bDrawDebug. So back over in the header, we can now create our new Boolean we've just mentioned, and be sure to provide this a U property, just so that we can easily update this if we want to remove our debugging information from the editor. So you'll be more than familiar with this type of thing by now, but we're just going to make this edit anywhere, and again provide it a category. And then finally, back in the code file, just in case you're using a different editor, be sure to remember to include the drawdebughelpers.h. Now, I'm using Rider for Unreal, which will add the files that it recognizes are needed for certain functions to be called, like the drawing debug things. So I already have this included, which is very handy. However, it's also decided that I might like the Windows platform features included, which I wouldn't, so I'm just going to get rid of that, and that should be ready to go, and begin testing in the editor. So let's go ahead and get that component compiled, and whilst that's happening, I'll just head back over to the editor and test those results. Okay, so with all of that done, I'm going to begin by duplicating an existing demo actor and ensure that it doesn't have any components that will conflict with our desired hover functionality. So for instance, deleting the floating component. Next, we can select to add a component, find the hover component from the options, and if we press simulate now, we can see that we're getting a warning message, which is informing us that the object is set to simulate physics on a static object. So this is that handy reminder that I mentioned earlier of why we want to set variables specific to a component through the component class, where possible, and if it's not going to completely disrupt the flow of the project structure. So rather than just setting this one object to be movable, let's head back to our code file quickly, and we'll make this update now, as we've seen a quick example of how this can save us time to make this a habit when working with these types of components. So like with our floating component, we're going to set the parent root mobility to movable through the setMobility function, and by setting the eComponent mobility option. So again, compile those changes. This one should be very, very quick, as we've just had a larger compile of the new class. With that compiled and ready, we can once again press simulate, and we can now see the cube drop. So if we select and move the cube around, we can see the distance that it's tracing to get the hover distance, but nothing is really happening, as we'll need to add some extra force in our exposed variable. We can also see here I have made a slight mistake. Now this one wasn't intended, unlike the previous one, but it's going to prove a useful example of simple things that can be easily overlooked. What we're getting is that we're still getting one warning about the mobility settings. You may have seen this as we're going through, so we're going to hop back to the code file one last time, and some of you, as I just said, may have spotted this during the initial implementation. Quite simply, what I've done is I've set the simulate physics to be true, one step before setting the mobility to be movable. Kind of needs to be done the other way around. So let's just move the mobility, swap that above, so that the set simulate physics call is below. And if we compile this one last time, that will fix all of our simulation and movement issues, and we can see now in the editor that all of those warnings have been resolved. So with all of that done, this is now more of a playground type thing. We can start testing all of the variables that we may want to set up for our hover component. So if we select our demo actor, and then select the hover component, we can easily change the things that we've exposed here. So we can start by increasing the hover distance, and we can see that that white debug line is extended. So it will be trying to apply that hover force from a higher point as soon as it is in that range of length. Then by increasing the hover force, we can see that it's starting to take effect and providing some hover feedback. Now, as I'm playing around with the variables here, you can see how easy it is to change the buoyancy and forces being applied. We can make it interact with anything providing a hit traceable collision type. So even the floating actors, you can get some pretty interesting results from having the floating actor move up and down, and having our hover component follow its movement. So that's pretty much it. You can now play around with your new component, see what kind of results that you can make from this. But with that working, we've now seen how to create two custom components, and we've seen some of the smaller differences between the actor and the scene component and how they might be used. You may have noticed that in both of these examples, you could probably easily change them out for the alternative option. And now that you've seen the differences between working with the parent actor location or the scene component location, you could give that a try to see what different changes you would personally need to make to get each one working as the other type of component. This has also shown you how the two most